Okay, so let's continue our discussion on group theory. I just want to use the color pen black. Uh, so this structure is such that I have modified the modules which are initial, and I reorganized modules. So just don't bother about the course schedule because I have modified the course schedule a little bit so that I want to continue giving the lectures on group 3. So to continue, so what we have seen so far is that there are this SU2, there is this SU2 group and its representations are determined, which are irreducible representations, are determined by using angular momentum algebra, very similar to determined by J and M values. For a given value of J, you can actually compute what the M values are, and accordingly we can compute the entire structure of the representations. Now, so the representations which we have chosen so far are, say, we have the examples we have seen are for J is equal to half, which is the fundamental representation, and then J is equal to 1, which is the spin 1 representation, which is okay, J is equal to half is a spin half representation, J is equal to 1 is a spin 1 representation, which is also called the adjoint representation. Adjoint representation. Then there could be other ones. So for example, what happens for J is equal to 3 by 2, what happens for J is equal to 2, and then you can have J is equal to 5 by 2 because it should be only half integers or integers, and so on, so on, so on, so on. Now, there is a very nice way which will be useful for us later on of there is something of presenting these representations. All this set of irreducible representations can be actually presented in a nice manner in something called the graphical representation. So let's look at these graphical representations. So the graphical representations are so the basic idea in the graphical representation is that in the quantum space or in some sort of a theory space in the quantum space, you represent all the irreducible representations according to their J values as well as per their M values. Okay, when I write it down, you will be clear. Say, for example, in the case of SU2, there is only one quantum number which is actually the labeling quantum number, which is the J3 or also the JZ actually, right? Nothing else is um, there is only one diagonal generator which is essentially the labeling generator. So whatever is the diagonal generator, we use it as the labeling generator, and the remaining ones would be your will be reconstructed into your raising and lowering operators. This is the basic technique of angular momentum, and this is what it has been used for also in the case of SU2. So let's say, so in the space of the diagonal generator, let's try to represent all possible meaning these representations in a systematic manner. So let's just take j is equal to half, and if j is equal to half, m takes the value minus half plus half. So let me write it this way. Okay, this is minus half, this is plus half. So the j is equal to half representation, the fundamental representation of SU2 can be represented by just a single line where the m values, or essentially the jz values minus half and plus half, are the endpoints of this particular representation. They form essentially the endpoints. Similarly, if we have g is equal to 1, I'll give you one more thing. So you'll have the values of m values would be minus j2 plus j. So it is total 2j plus 1 values. So minus 1, 0, 1. So this is another representation which is sort of what we have seen as the adjoint representation. This is the fundamental representation, is the adjoint representation. So a given representation, say for example, if somebody tells you that okay, I draw a straight line with minus half plus half, so that would be your fundamental representation of SU2. Similarly, if adjoint would be having minus 1, 0, 1. So this is the same representation which we have seen, but instead of presenting all the matrices and all the details and everything, we just represent it in a way which is just in graph, in some sort of a graphical manner, in the space which is of the JZ space. If you want, it's a JZ space. So what happens to j is equal to 3 by 2? So j is equal to 3 by 2. We will have 4 values, because minus 3 by 2 minus half plus half 3 by 2. Okay, similarly, and so on, so on, so on. So as of now, meaning it will not be very evident why I introduced to you this graphical representation, but later on this will be extremely you will realize that there is some connection in the way we organize particles in the hadronic sector. This is all sort of preparation for the hadronic spectrum, understanding the spectrum of say mesons or baryons. So this graphical presentation of group representations would be very useful there. Okay, so that's the basic. So various representations of the group can be represented graphically is the basic point I wanted to mention. So so I said for SU2 you can have these kind of representations which are graphically, and this will come back to us later on actually. So finally, before I close, I would like to just say that okay, the advantage of this graphical representation is that you have the raising and lowering operators, say for example j plus minus, move along this line, say for example j plus minus, j plus. So j plus, say for example, acting on this line will keeps jumping from one point to another, and j minus will keep jumping from another point to another. So say j minus would be acting in the opposite direction, reducing one point to another actually. Okay, so this we can see this entire aspect of constructing these representations and the action of the raising and lowering operators directly graphically. Okay. And there are other advantages also for this. For example, if you multiply two representations, the direct product of two representations would give you some okay. This will be useful for us later on. Say, for example, if we have two spin half particles, say for example j is equal to half times j is equal to half. This, by using angular momentum algebra, should give you j is equal to 1 plus j is equal to 0. Okay, this is addition of angular momentum. So this is precisely what we can see graphically also. So in the graphical picture, if you have j is equal to minus half plus half, now this into minus half plus half. Now the way you do it is you take say for example this is a particle A with spin half, particle B with spin half. Put B on both endpoints of A. Say for example we still have A here, minus half plus half. So this is A, this is B. Now you sum this endpoint values. Say for example this gives me summing or putting B over this endpoint gives me 0 and 1. Now you put it back onto on this endpoint. Okay, minus half plus half minus half plus half. This is B and this is A, and this gives me minus 1 0. Okay, so the addition of the angular momentum gives me two spin half particles, gives me a particle which is minus 1 1 0 1 and another one with a 0. Because 0 is repeated, you can actually see it as this essentially ends up being minus 1 0 1 and just 0. So you can actually do addition of angular momentum also graphically. Okay, but okay, whatever I have shown the simple relation that if you have two spin half, you'll always end up having with one spillward particle and one spinless particle. So this is what I have shown, but this also can be done graphically in the procedure I have shown. So if you have two spin half particles, so you place the second spin half particle over the edge of the other, some or all possible m values. Okay, this is essentially doing the same thing as we do, because we also sum over all the possible m and m value. In this, it's okay. You sum over all the possible m values. So this gives me plus half is 1, minus half half, that is 0, and we place it over the second center, which gives me a minus half that is minus 1, and half minus half, that is 0. So it gives me essentially a representation with minus 1 0 1, and then there is 1 which is spinless, spin 0. So these are the main advantages of the graphical representation. So you can actually, like I said, you can see that the dimension of the representation, which is either two-dimensional, which is essentially 2j plus 1 two-dimensional in the case of fundamental, or three-dimensional in the case of adjoint. or 4 dimensional in the case of 3 by 2, and then you have the operations of j plus and j minus acting on each other, and then you can also look at addition of angular momenta and stuff like that. Finally, one final comment on SU2. The representations of SU2 are actually pseudoreal. That means they are real, so they are not complex representations, not complex representations. What it means is that so uh, every representation and its complex conjugate are the same. Every representation its complex conjugate are the same representation. But the problem is there is no basis in which you can show that it is true. Okay, what it means is that um, so suppose the representations of SU2 are say J, say for example J. So that means there is always a similarity transformation as J, all the J's, S inverse is equal to J star. Okay, maybe there is a minus sign or something. Okay, so you can always go into a basis. You can always go using a similarity transformation where the generators of SU2 are and their complex conjugates are essentially the same. So okay, so the only thing is they are called. This means that they are real representation. The representations of SU2 are real, but unfortunately there is no real. There is no basis. Okay, there is no basis in which this can be shown clearly. That's the reason why they are called pseudoreal. Where this can be explicitly be shown. And that's the reason why they are called pseudoreal. The representations of SU2 are pseudoreal. So as long as you can have a similarity transformation which transforms the generators to their complex conjugates, the corresponding representations are called real representations. For SU2, such a transformation exists. There is a similarity transformation exists, but there is no actual basis where you can actually show that all the generators are real. Okay, the generator, there is no basis where this can, what I mean to say is this can be shown means there is no basis where you can have all the three generators real. Where all three generators are real. So at least one of, say for example, typically sigma 2 is shown to be imaginary. Okay, so it is all the three generators should be real in principle, but there is no basis in which all the three generators are real. So that's the reason why it is called a pseudoreal basis. Okay, pseudoreal representations, but in reality, for all practical, the SU2 is actually a real representation. So, for example, the fundamental, which is a two-dimensional representation, is equal to two star representations or two bar representations. The fundamental and the anti-fundamental are the same representation, or the complex conjugate representation. Okay, or sometimes it's also called two bar or complex conjugate. Okay, both these representations, they are essentially the same representation, the same representation. There is no difference between 2 and 2 bar, or 3 and 3 bar, or 4. Say for example, spin 3 by 2 and spin 3 by 3 2 bar, or a 4, essentially 4 dimension, and 4 and 4 bar are the same representation in SU2. So all the irreducible representations of SU2 are and their and the corresponding complex conjugate are equivalent to each other. So this is the final comment I wanted to make about SU2 uh, before moving to SU3. Okay, this is important because in what happens in SU2 uh, becomes more complicated in SU3. That's precisely the reason why I wanted to stress this particular point actually. Okay. Now, the other group which we would be very interested is the SU3 group. We'll start with that now, actually. And if you have any further questions on SU2, uh, just put them when we do the contact hour next week, so we can have um, uh, a discussion there, actually. So SU2 is somehow a much simpler group, uh, but the real complexity of group theory and everything will start appearing in SU3. This group is also important for us because we'll use this a lot in understanding strong interactions, which will be the next topic which we'll be dealing with actually. So SU3 is a group of all unitary matrices which are three-dimensional. Okay. Now let's just look at so for a general n, we know how many free parameters are there. Okay, for a general SUN, there are n square minus 1 free parameters. This you can just okay, check it by looking at say taking an n by n unitary matrix. So if you take an n by n unitary matrix, complex matrix, so you have how many complex parameters? So there will be two n real parameters. and then you have u dagger u is equal to 1, which gives you n square conditions, and then there is the det u, which is equal to plus 1, which gives you one more condition. So you end up having n square minus 1 real parameters, which specify a unitary matrix in n dimensions. Okay, so given that you have n square minus 1 free parameters for SU3, you'll have n square, so 3 square minus 1, so that is 8 free parameters. So that means we have 8 generators, and it's a 3 by 3 matrix, right, essentially. So it has 3 by 3 complex entries. So u, so 3 by 3 is equal to exponential I, so theta a lambda a, where lambda a are the generators of SC3 group. These lambda a are called GLIMAN matrices, after Mulle Gell-Mann, who actually did it long ago. Actually, one of the first ones who did it in the 1960s. So he introduced all these things for okay. So there are 8 generators. So lambda a would be 8 generators. So this, let's explicitly write down these 8 matrices. The initial ones look very similar to the Pauli matrices, and except for a couple of them. So we'll see which ones actually. So this has been very cleverly done by Gell-Mann actually. The Gell-Mann matrices are the following: lambda 1 is equal to 0, 1, 0, 1, 0, 0, 0, 0, 0. Lambda 2 is equal to 0 minus I, 0, I, 0, 0, 0, 0, 0. Lambda 3 is equal to, so this looks like adding a row of zeros to the first three essentially is adding a row of zeros to the Pauli matrices. 1, 0, 0, 0 minus 1, 0, 0, 0, 0. Then lambda 4 is also very similar, but okay, I'll just write it down so that you learn. Lambda 4 would be, but now at the this one essentially at the middle row. Okay, 0, 0, 0, 1, 0, 0, lambda phi 0 0 minus I 0 0 0 I 0 0, and then lambda 6 is again on the top row. So the third one is not written, actually 0 0 1 0 1 0, and lambda 7 0 0 0 0 0 minus I 0 I 0, and lambda 8 has this peculiar normalization, which is root 3 1 0 0 0 1 0 0 0 minus 2, as expected. Okay, all these matrices uh, are traceless Hermitian as expected, because okay, all these matrices are traceless and Hermitian. All the generators because they sit in the exponential of an because they represent an exponential of purely because of u is equal to e power I h, because that's the case. Every unitary matrix can be represented and everything represented by as an exponential of a Hermitian matrix, and that u is equal to plus 1. Both these conditions fix the tracelessness and the Hermitian properties of this one. And these generators, 8 of them, they are 3 by 3 as expected, because it's a group of 3 by 3 unitary matrices. And so the generators are also 3 by 3. This is in the fundamental representation. This is the fundamental representation of SU3. The normalization of the generators is such that trace of lambda A, lambda B is equal to 2 delta AB. Product of the two is such that it's equal to 2 delta AB, and the important property of the Lie algebra is the commutation relations of the generator. Okay, so the commutation relationships of the generator are essentially are the structure constants of are determined by the structure constants of the group SU3. They are given by lambda A by 2, lambda B by 2 is equal to I FABC lambda C by 2, where FABC is the structure constants of SU3. FABC is completely is the structure constants. Okay, let me just mention that is the structure constants of SU3. So So the SU3 also have their own Lie algebra. Okay, they also satisfy the Lie algebra. So exactly like in SU2 case, because any continuous group, unitary continuous group, would have essentially the same meaning the same form of the commutation relationships, and where these constants would differ with the number of generators and the constants would differ. For each group essentially, like I mentioned in the previous lecture. The structure constants of SU3, again these FABC are completely antisymmetric. And they're actually determined completely. So let me write it down, these structure constants for completeness. So whenever, because they're completely antisymmetric, so whenever the index repeats, say for example when A is equal to B or B is equal to C, okay, that structure constant is 0 because it's completely antisymmetric in ABC. Complete and in A, B, C. So when A is equal to B or B is equal to C or A is equal to C, or all of them are same, or any of these cases, the structure constant just vanishes. So the non-zero um, components of FABC are, okay, say for example F123 is equal to 1, 147 is equal to half, F156 is equal to minus half, F246 is equal to again half, F257 is equal to half, F345 is equal to half, F367 is equal to minus half, F458 is equal to root 3 by 8, root 3 by 2, sorry. F678 is equal to root 3 by 2. So these are the only non-zero structure constants. The rest of them all zero. So we don't really have to worry about what happens. Say, for example, 256. Say, for example, 256. 256 is zero. But 257 is non-zero. Okay. So similarly, so the only non-zero ones are essentially these are the elements. Now we can ask the question, how to construct the representations. So okay, again what we have to ask the question, how to construct the representations of SO3. Now we ask the question how to construct sp3 representations, which are sp3 irreducible representations of sp3. This we want to follow the same methods which we have used for SU2, because we want to use the same angular momentum algebra sort of technology. Okay, we want to use the same angular momentum technology, and that makes things easier because we can use the same technology as we have done for SU2. Now, for that, we have to see what would be the corresponding labeling operators. Okay, labeling operators, and what would be the corresponding raising and lowering operators. Now, if you look at the generators, now we see that if I use the eigenvalues of lambda 3, there are two diagonal generators compared to SU2, which has only one diagonal generator. In this case, the two diagonal generators are lambda 3, okay, which has the same thing as sigma 3 but with a 0 and the 0 row, and then the lambda 8. Okay, so there are these two operators which are lambda 3 and lambda 8. So both of them will be needed to construct a representation. Um, so there will be two eigenvalues corresponding, unlike the case of uh, unlike the case of say SU2, where there is only one eigenvalue. It's essentially J in the case of SU2. Okay, there is only J in the case of SU2. Here you have some sort of J1 and J2, but J1 and J2 are different things. One is a different set of eigenvalues, another is a different set of eigenvalues. So it is not exactly J1 plus J2 sort of thing. So you'll have J1 or J would be something like lambda 3, and lambda 8 is a different set of eigenvalues. If you look at lambda 8, it is 1 minus 1 1 minus 2. So it is a completely different set of eigenvalues it will have, and also within a different normalization. So one has to be a bit more defined. Okay, so you need two different um, uh, uh, meaning labeling operators, lambda 3 and lambda 8. One advantage is immediately you can see that lambda 3 and lambda 8 commute with each other. So you can actually use it for labeling irreducible representations. So lambda 3 and lambda 8 commute with each other. One important observation is that so lambda 3, lambda 8, maybe you can put a half on both sides, is equal to 0. They commute with each other. So they can be diagonalized simultaneously. And so what if you can diagonalize, they can be diagonalized simultaneously. And thus they can be used as labeling operators. Now we can define several raising and lowering operators. Okay, several raising and lowering operators immediately. So first you can define something like T plus minus is equal to. So T is essentially a raising and lowering operator. For example, in the case of lambda 3. Okay, so this can be represented as lambda 2 plus minus lambda 1 plus minus I lambda 2 by 2. Okay, So this is a raising and lowering operator for eigenvalues in lambda 3. Okay. So that is one thing. Then you can have u plus minus is equal to, there should be one raising and lowering operator in the in 6 and 7 also. Say for example, okay, so lambda 6 and 7, if you remember, 6 and 7 are in, so for example, in the bottom 2 by 2 block of lambda 8. So in the bottom 2 by 2 block of the lambda 8, you can have the raising and lowering operators. So this would be lambda 6 by 2 plus minus I lambda 7 by 2. Then you can have another raising and lowering operators which involves 4 and 5. So 1 and 2 would be only in the lambda 3. Lambda 8 actually also can have an opposite direction. So for example, so you can have 4 and so lambda, oh sorry, I'm sorry. So this is moving too fast. So one we need, say for example, a raising and lowering operator in the bottom 2 by 2 block of lambda 8. Okay, so you can have one of that. Then there is one in the remove, if you suppose if I remove the second row and second column, you can also have one more raising and lowering operator. Okay, between 1 and 3. Okay, between 1 and 3, and that raising and lowering operator is given by 4 and 5. So for corresponding lambda 8, you have two raising and lowering operators, one corresponding to the bottom two block, another corresponding to the 1 and 3. 1 and 2, there is already one lowering operator uh, in actually given in 1 and 2, right, for example. So you have the third raising on operator. Okay, so we, let me call this as V plus minus is equal to lambda 4 by 2 plus minus I lambda 5 by 2. So we constructed for the diagonal basis, there are three raising and lowering operators, one corresponding to 1 2, one corresponding to 1 3, which is V, and other corresponding to 3 parts of the diagonal matrix. Essentially, if you want, you can think in this particular terms. Now one can derive the computation relations between these three essentially. So for example, between it becomes a bunch of computation relations. Uh, Relations can be derived in terms of uh, okay T3, okay, U3 and V3. So for example, if I okay, you can in terms of T plus minus, V plus minus, U plus minus, which are the three raising end operators. And then suppose if I define T3 is equal to lambda 3 by 2, and then I define Y is equal to 2 by root 3 lambda 8 by, oh no, that's enough, lambda 8 Y is equal to, then we have a bunch of uh, computation relations which you can write them down essentially. Exactly like we want to put everything in terms of the notations of SU2, but now things become complicated because compared to SU2, SU3 is a much larger group. Its rank is 2. SU2 has rank 1. SU3 has rank 2. So that is the reason why that means it has two diagonal generators. So in principle, you can have raising and lowering operators in all possible more raising and lowering operators, and there is also further complication in SU3 is that its representations are complex. That means its there is no similarity transformation which takes its representations to the complex conjugate of its generators to the complex conjugate complex conjugate of those generators. Say for so the representations of the complex conjugate of the generators are not the same as the representations of the odd or normal generators. So I won't write down all possible uh, commutation relation. Let me write down a few commutation relations just for completeness essentially. So just to see how the raising and lowering operators work on. Okay, so we have T3 going into T plus minus. This is exactly like in SC2 because this is SC2. Then there is y t plus minus is equal to 0. Y is, remember, lambda 8. So lambda 8 will not get y because lambda 3 and lambda 8 commute. The t plus minus doesn't really act on y. Okay, so that's one thing. Now T3 acting being acted by u plus u minus minus half plus minus u plus minus T3 acting on v plus minus, okay, half v plus minus. You remember is the representation with respect to u is the representation. Some of the commutation relations are essentially uh, given as follows. T3 u is lambda 6 lambda 7. Now this also gets modified because this modifies the T3 givens in terms of acting upon T3 will give me this particular relation. So u also will give me this particular relation. Now T3V, so we have seen how T3 acting on the raising and lowering operators T, U and V will act. Now let's just see what happens with the Y. So Y acting T plus minus will just give me 0. Y similarly Y acting on U plus minus will give me plus minus U plus minus. Okay, Y acting on V plus minus gives me plus minus V plus minus. Okay, so then there are other bunch of relations like a T plus T minus commutator would be giving me 2, 3. U plus U minus will be giving me 3y by 2. Okay, so this is the reason why this will become clear why this happens, because if you look at T plus T minus, it is actually 2T3. Now, but if you look at U plus U minus, the commutator is actually both, it acts both, it changes both Y as well as T3. Sometimes you can call this as 2U3. Okay, this T3 minus Y, 3 by 2 Y as U3. Okay, and so again V plus V minus commutator is also non-zero, which is 3 by 2 Y plus T3. Sometimes you call it as 2V3 in notations actually. So what does, so to summarize all these things essentially, so T plus raises T3 by 1 unit and leaves Y unchanged. So that means lambda 8 is completely independent of T plus, the raising and lowering operators of T plus at T3, whereas U plus lowers T3 by half, okay, remember, okay, and raises Y by 1 unit. And V plus raises T3 by half and lowers, raises Y by 1 unit. And similarly you can look at what happens for T minus and T plus and so on. So the raising and lowering operators are slightly more complex compared to SU2. Okay. Uh, because there are now 3 raising and lowering operators. So graphically, let's just see what happens in the graphical representation. This becomes interesting from now on actually. Suppose if in the two eigenvalue axes now we have our Y and then T3. So then you have on the T3 direction there is T plus, which keeps increasing it, and then this side lowering it would be T minus. The other two raising and lowering operators would now act diagonally. So for example, U plus will start increasing Y by 1 unit and okay, so something, and reducing T3 by half unit, whereas U minus would act in the opposite direction. V plus also raises Y by 1 unit, but it also increases T3 by half unit. Okay, it also increases by half unit. So it's exactly not diagonal in the sense that Y value of Y's and delta Y and delta T3 will be the same, but delta 3 is equal to half, T3 is equal to half, and delta Y is equal to 1. So this will be V minus. So it's not exactly diagonal, but they act in the diagonal space, diagonal direction in the T3 Y space. So they are not exactly at 45 degrees. So their angle is about 60 degrees, say for example, because one is one is the double of the other, meaning in one direction, the slope is one direction, double of the other. Now, so this is some sort of graphical representation. How you can construct the of SC3. Okay. So now let's look at now every SC3 representation actually is characterized by two quantities which are two integers which are called P and Q. Now, generally, what we have seen in the case of say for example SU2, every say for example if you have this kind of a thing, every boundary is every element or you call every point in the graphical line is occupied by one particular state. Essentially, it's a characteristic. Okay, that essentially determines your the dimension, and that also determines the multiplicity of the particles. Okay. In the case of SU3, that is not true actually. I'll come back to it when we are discussing uh, uh, when you are discussing the eightfold way or the what do you call as the decuplet and nanoplet. But as of now, the in what happens in SU3 representations is that multiplicity is not actually single, but there could be several states. So states in this boundary are essentially occupied by they are singly occupied. The second layer is essentially doubly occupied, and third layer is so on. So essentially, so until there is some limit, on the number of particles you can have at a site actually. So there is some the representations are not exactly the same, but typically these representations are represented by two co-numbers. Numbers P and Q, which are lengths of the some sort of a polygon pattern. Actually, the representations are essentially end up being some sort of a polygon pattern in this graph. Say for example, say if you have a representation which are lengths of the polygon in the T3y plane. So this will be a representation P, Q, P, Q. So this is a representation PQ. Remember that PQ representation is a essentially these are some sort of lengths. It's not exactly equivalent to the eigenvalues of lambda 3 and lambda 8, but this is some sort of a hexagon in the which whose lengths are essentially p and q, this one. Say for example, to give you a more idea, um, so the fundamental representation um, is just given by and the anti-fundamental is given by this, where these are equilateral triangles in this way. P is equal to 1 essentially in this case and Q is equal to 0. In this case P is equal to 0 and Q is equal to 1. This is essentially anti-fundamental representation, whereas this is a fundamental representation. So this is 3 is essentially PQ is equal to 1, 0 and 3 bar is equal to 0, 1. So this is actually a very nice way of a very easy way of uh, uh, a very convenient way of representing all possible representations of SU2 essentially SU3, and the dimension of each representation is given in terms of this D P in terms of this P and Q. In this particular, using this particular formula, P is equal to P plus 1, Q plus 1, P plus Q plus 2 by 2. Okay, so this is essentially the P and Q. If they are unit ones, there are sort of lengths in this T3 plane, which give you essentially the representations, all possible representations. This is a 3 representation, this is a 3 bar representation, and with a dimension here, if you take Q is equal to 0 and P is equal to 1, it gives a dimension actually 3, the fundamental representation. So this way you can classify all possible representations of SU3. For example, another interesting representation would be when P and Q are equivalent to 1. So this is called the octet representation. Then PQ is equal to 1, 1. This is an octet. Another representation when is called a decuplet representation. Which has 3, 0, which is dimension 10. Where P takes the value 3, so this gives me the decuplet representation of so this is called the decuplet representations. Now there is actually a method which you can actually derive all these representations in great detail. Uh, what is important is to summarize is that SU3 is slightly more complicated. Um, the representations are planar, they are not single line, so they are not linear or in a single line, they are planar, and their representations, because you have two, actually three raising and lowering operators and two labeling operators. Okay, two labeling operators, one in x and one is one direction. So there are in one x direction there is one raising and lowering operator and two diagonal raising and lowering operators. Because of this, the representations end up being planar. I didn't derive the bounds on this, uh, meaning on this x and y. They can actually be done using the same technology, but the bounds are essentially represented in terms of these quantities which are called p and q. For a given dimension, you have this p and q, which essentially give you the length of these objects, which are essentially hexagons and hexagons or polygons um, uh, in the two-dimensional space essentially. Okay, these are hexagons and triangles and inverted triangles, dominantly triangles and inverted. The triangle is essentially a in which the p takes a value and q goes to 0, the inverted triangle, and the triangle is when p goes to 0 and q goes to some value essentially, whether it's a 3 or 1, 2, 3 and so on. So essentially when p goes to 1, that the triangle is called the fundamental representation, which essentially is the 3 uh, representation or 3 star, and when p goes to 0 and q goes to 1, then it is the anti-fundamental representation, which is essentially a triangle given in this particular fashion. In when the p and or q takes unit values, those are essentially of unit length, these triangles, and these are the fundamental representations of SU3, which are, and again remember that the 3 and 3 bar are not the same representation, their complex conjugates are not the same. Okay, one is a representation of lambda, which are the GLIMAN matrices, another is a representation of lambda star, which is the anti-fundamental. The two other interesting representations are essentially the 8-dimensional representations, okay, which is also the adjoint, which has this particular form of a hexagon, uh, which is called an octet. It has 8 sides, where the two sides, okay, 1, 2, so we have to put the sides right because it's 8-dimensional. So the two of the sides are at the center of the this hexagon, where the other 6 sides are the boundaries. The other interesting uh, representation is the 10-dimensional representation, which is also called the decouplet, which is like a inverted Pascal triangle essentially, in which the p takes the value 3 and q is equal to 0. So it is one. There are 4 sides along the 2 sides and all the 3 sides. Okay, and 1 side in the center. Okay. So so this is how we build irreducible representations of SU3. Okay, SU3 irreducible representations are slightly complicated, but you can. There are other methods like the tensorial method, which actually constructs all these representations and computation of the dimensions. But that is way beyond our mandate. But we don't really have to study all of it. Okay, so so far what we have looked at is that the representations of SU3, irreducible representations of SU3 are planar. That's our take home message. And they have these shapes which are essentially like inverted triangles and hexagons and the inverted triangle, which is 10 dimensional, has 10 sides, and this hexagon has essentially 8 sides, and for the SU3. Now we will see where these things will appear in particle physics. Okay, in the next lecture or so, we'll start looking at where these things will start appearing in particle physics, and what is the ingenuity of these great guys like GLIMAN and company, who use this philosophy to get this entire uh, SU3 picture, understanding of the group theory of SU3 in such great detail actually. Okay, so I'll stop my lecture here, and in the next lecture I'll just try to show some theoretical examples of how these symmetries appear in various cases essentially. Okay, especially in the case of degenerate masses. So this is what I will try to show, and then we'll see actually how then we'll go to strong interactions, understanding of the strong interactions. So let me stop my lecture here.